1908, Highland Park, Michigan. Through the steam and grinding of America's largest manufacturing facility, European automotive engineers watched something that defied every principle they held sacred. A 27-year-old Danish immigrant named Charles Sorensen was casting engine blocks using methods that luxury manufacturers like Mercedes-Benz and Rolls-Royce declared would destroy quality forever. Mass production destroys precision, insisted Wilhelm Maybach, Europe's most respected engine designer. Hand-fitted components and meticulous craftsmanship, that's what created engines worthy of $3,000 price tags. But Sorensen's thick-walled cast iron blocks, churned out at 1,000 per day, were doing something impossible. While European luxury engines required complete rebuilds at 50,000 miles, these mass-produced American blocks were running 300,000 miles without failure. Today's advanced aluminum engines, with computer modeling and precision manufacturing, crack at 100,000 miles. Somehow, the immigrant foundry worker had discovered something that modern engineers still don't understand. The letter arrived at Daimler Motoren Gesellschaft headquarters in Stuttgart on a crisp October morning in 1908. Wilhelm Maybach, chief engineer and the mind behind Mercedes luxury automobiles, read the intelligence report with growing disbelief. American automobile manufacturers were attempting something that violated every principle of quality engineering his 30 years of experience had taught him. They plan to cast entire engine blocks as single units, Maybach announced to his assembled team of master craftsmen. The workshop fell silent. For decades, European manufacturers had built engines the proper way, individual cylinders, each hand-fitted to exacting tolerances, assembled with the precision that only master metalworkers could achieve. A single Mercedes engine required 6 months of careful work, justifying its $3,000 price tag. Impossible, declared Hans Ledwinka, Maybach's senior metallurgist. Cast iron cannot maintain the precision tolerances required for reliable compression. The porosity alone would render such engines worthless within months. Maybach nodded gravely. European automotive engineering had evolved through centuries of metalworking tradition. Each component was individually crafted, tested, and fitted by specialists who understood that quality demanded time, skill, and the personal attention that only human hands could provide. The Americans, with their crude industrial methods, seemed determined to sacrifice everything that made automobiles worthy of the name. 8,000 miles away, in Highland Park, Michigan, Charles Sorensen stood in the center of what would become the world's most revolutionary foundry. At 27, the Danish immigrant possessed an intuitive understanding of metallurgy that university-trained engineers often lacked. His massive hands, scarred from years at Buffalo's Jewett stoveworks, moved across the wooden patterns that would soon become obsolete. "Charlie, they're saying it can't be done," Henry Ford said, his voice carrying the weight of mounting skepticism from investors and competitors alike. 1,000 engine blocks per day, each one better than what Mercedes builds by hand. Sorensen examined the prototype Model T block, its thick walls and monolithic design representing everything European engineers considered impossible. The casting weighed 240 pounds, nearly twice the weight of comparable European engines. Where Mercedes built thin-walled blocks requiring precise tolerances, Ford's design embraced thickness that could absorb stress and thermal cycling. "Weight means strength, Henry," Sorensen replied, running his fingers along the rough casting. "They build for precision. We build for endurance." The Highland Park factory stretched across 60 acres, making it the largest manufacturing facility in the United States. Inside, 15,000 machine tools waited to transform Sorensen's castings into engines that would power America's automotive revolution. But first, the foundry had to prove that American methods could match European craftsmanship. Early production revealed the magnitude of the challenge. The first Model T block suffered from porosity that validated every European criticism. Inconsistent metallurgy created quality variations that sent rejection rates soaring. Workers struggled with assembly line methods so foreign to traditional craftsmanship that labor turnover approached 380% by late 1913. Perhaps the Europeans are right, admitted P. Martin, Highland Park's plant superintendent, as he surveyed another batch of defective castings. Quality and speed may be fundamentally incompatible. But Sorensen refused to accept defeat. He understood what European engineers missed, that durability came through design, not decoration. While Mercedes engineers obsessed over surface finish and precise tolerances, Sorensen focused on the molecular structure of cast iron itself. Gray cast iron, he discovered, possessed a tensile strength of 25,000 pounds per square inch, significantly stronger than the modern aluminum alloys that would replace it decades later. The secret lay not in rushing production, as Europeans assumed, but in understanding the chemistry of metallurgy at an industrial scale. Every casting teaches us something, Sorensen told his foundry workers, most of them immigrants like himself who understood that American opportunity demanded proving themselves against European skepticism. We're not just making engines, we're proving that American methods can create superior products. The breakthrough came through understanding what European foundries couldn't replicate in small batch production: controlled cooling cycles that optimized graphite formation within the iron matrix. While European foundries rushed their cooling process to meet hand assembly schedules, Ford's mass production allowed time for proper metallurgy. 24-hour cooling cycles created graphite structures that European craftsmen, working one engine at a time, could never achieve. By late 1910, even Ford's supporters began to doubt. Could American industrial methods really compete with centuries of European tradition? Production targets were missed. Quality control failures mounted. Critics pointed to every defective casting as proof that mass production destroyed the artisanal excellence that defined automotive engineering. In Stuttgart, Wilhelm Maybach read the latest intelligence reports with satisfaction. American shortcuts lead inevitably to American failures, he declared to his engineering staff. Quality cannot be mechanized, it must be crafted. But in Highland Park, Charles Sorensen was discovering metallurgical principles that would revolutionize not just automotive manufacturing, but the entire relationship between American industrial innovation and European traditional craftsmanship. The foundry crisis that threatened to destroy Ford's vision of the universal car was about to become the proving ground for engineering superiority that no one, not even Sorensen himself, could have predicted. The breakthrough came at 3:17 in the morning on February 14, 1911. Charles Sorensen stood in the Highland Park Foundry, watching molten iron flow into the massive casting molds that would create Ford's revolutionary engine blocks. The foundry operated around the clock now, its furnaces glowing like industrial cathedrals in the Michigan darkness. "Charlie, the cooling rates are still inconsistent," reported James McLeod, the foundry's lead metallurgist. "The thick sections cool too slowly, the thin sections too fast. We're getting internal stress fractures." Sorensen nodded, his mind racing through metallurgical calculations that no European engineer had ever needed to consider at this scale. Traditional foundries cast 1 or 2 engine blocks per day, allowing craftsmen to monitor each casting individually. Ford demanded 1,000 blocks daily, a production rate that required completely reimagining the relationship between heat, time, and iron chemistry. "We're fighting the metal instead of understanding it," Sorensen replied, examining a cross-section of failed casting under the foundry's new electric lights. The internal structure revealed the problem: uncontrolled graphite formation that created weakness instead of strength. European engineers built thin-walled blocks because they understood precision tolerances. But Sorensen was discovering that Ford's thick-walled design offered advantages that traditional craftsmen couldn't exploit in small batch production. Gray cast iron contained approximately 92% iron, 3.4% carbon, 2.5% silicon, and 1.8% manganese. The carbon content was crucial. Too little created brittle white iron, too much caused excessive shrinkage. "The graphite flakes are forming randomly," Sorensen explained to P. Martin during the morning shift change. "In traditional castings, that doesn't matter because the blocks are small, but our castings are massive. We need controlled graphite distribution throughout the entire structure." Martin studied the metallurgical charts Sorensen had developed through countless failed experiments. How do we control something that happens inside molten metal? The answer lay in understanding what European foundries had never needed to master: the relationship between cooling time and graphite formation at industrial scale. Traditional foundries rushed cooling to meet hand assembly schedules. But Ford's mass production created an unexpected advantage: time for proper metallurgy. Sorensen instituted 24-hour cooling cycles that allowed graphite to form in optimal patterns throughout the iron matrix. The slow cooling created flake structures that acted as internal lubricants, reducing wear while maintaining structural integrity. European craftsmen, working one engine at a time, could never achieve such controlled metallurgy. "We're not just making engine blocks," Sorensen told his foundry crew during the shift meeting that would change automotive history. "We're engineering the molecular structure of iron itself." By March 1911, the results began validating Sorensen's revolutionary approach. Ford's thick-walled blocks demonstrated tensile strength exceeding 25,000 pounds per square inch, substantially stronger than European thin-walled designs that relied on precision fitting rather than material strength. The graphite flakes that European engineers feared as imperfections actually enhanced durability through microscopic lubrication. The Highland Park Foundry became Sorensen's metallurgical laboratory. 15,000 machine tools, including specialized milling machines that could load 15 engine block castings simultaneously, shaped the rough iron into precision components with unprecedented speed. Each machine was positioned to minimize material handling while maximizing production flow, a manufacturing philosophy that European craftsmen found incomprehensible. "They're treating engineering like farming," Wilhelm Maybach observed in a letter to Gottlieb Daimler after reviewing intelligence reports from Highland Park. "Mass cultivation instead of individual artistry. It violates everything we know about quality manufacturing." But Sorensen's farming approach was revealing metallurgical principles that traditional craftsmen had never discovered. The controlled environment of mass production allowed precise monitoring of carbon content, cooling rates, and graphite formation patterns. Each casting provided data that informed the next 1,000 castings, a feedback loop impossible in artisanal production. Henry Ford visited the foundry daily, watching Sorensen transform his crude sketches into manufacturing reality. "Charlie, the Europeans are saying we're destroying quality with quantity. Are we proving them wrong?" Sorensen gestured toward the production line where finished engine blocks moved with mechanical precision toward final assembly. "Henry, we're proving that American methods can create superior products through understanding materials, not just working them." The validation came through endurance testing that European manufacturers had never attempted at scale. Ford's test engines ran continuously for hundreds of hours, while European luxury engines failed within days of similar stress. The thick-walled design absorbed thermal cycling that destroyed thin-walled competitors, while the optimal graphite structure actually improved with age. "Our blocks get stronger through use," Sorensen reported to Ford's Engineering Council in June 1911. "The controlled graphite formation creates microscopic lubrication that reduces wear. European blocks weaken through thermal stress. Ours strengthen through thermal conditioning." The Highland Park Foundry was producing engineering results that challenged fundamental assumptions about quality and craftsmanship. European manufacturers built individual engines with precision tolerances measured in thousandths of inches. Ford built thousands of engines with material strength that rendered such precision unnecessary. By late 1911, field reports confirmed what foundry testing had predicted. Model T engines were demonstrating reliability that European luxury automobiles couldn't match. The thick cast iron blocks that Mercedes engineers dismissed as crude American shortcuts were outlasting handcrafted engines costing 10 times more. Wilhelm Maybach received these reports with growing concern. If American methods truly produce superior durability, what does that mean for European automotive leadership? In Highland Park, Charles Sorensen was discovering that the answer lay not in traditional craftsmanship, but in scientific understanding of materials at scales that European artisans had never imagined. The Foundry revolution was creating engines that would redefine automotive engineering for the next century. The microscope revealed what would transform automotive engineering forever. In the Highland Park Metallurgy Laboratory, Charles Sorensen peered at a cross-section of Ford's gray cast iron, magnified 400 times. The structure looked like a frozen river delta, graphite flakes branching through the iron matrix in patterns that defied everything European metallurgists understood about cast iron weaknesses. "James, look at this," Sorensen called to McLeod, pointing at the microscopic landscape. "The graphite isn't random. It's forming networks throughout the entire structure." McLeod adjusted the microscope focus, studying the intricate patterns that mass production cooling cycles had created. In traditional castings, we see scattered graphite particles, but these look almost organized. This was the discovery that would separate American foundry science from European craftsmanship forever. The slow cooling that Ford's production schedule allowed created graphite flake networks that acted as internal lubrication systems. While European engines relied on external oil to reduce friction, Ford's blocks contained microscopic lubricants distributed throughout their molecular structure. "It's self-lubricating iron," Sorensen realized, the implications staggering him. The material itself reduces wear as it operates. By August 1912, Sorensen had perfected the cooling process that created optimal graphite distribution. The Highland Park Foundry maintained precise temperature control throughout 24-hour cooling cycles, allowing carbon to separate from the iron matrix in controlled patterns. European foundries, constrained by small batch schedules, rushed cooling and created random graphite distribution that weakened their castings. Ford's metallurgical formula had evolved through countless experiments into a precise science. 92% iron provided structural strength. 3.4% carbon created graphite lubrication. 2.5% silicon enhanced fluidity during casting. 1.8% manganese improved hardenability. But the real breakthrough was understanding how cooling time affected the interaction between these elements. "Temperature controls everything," Sorensen explained to Ford's engineering team. "Cool too fast, and the carbon forms brittle carbides. Cool too slow, and we get excessive graphite that weakens the matrix. But cool at exactly the right rate, and we get graphite flakes that strengthen the iron while reducing friction." The Highland Park Foundry had become a metallurgical laboratory operating at industrial scale. Temperature sensors monitored cooling rates throughout the massive casting molds. Chemical analysis verified carbon content in every batch of molten iron. Quality control measures tracked graphite formation patterns that traditional craftsmen had never needed to understand. European foundries operated on centuries of accumulated wisdom about working iron by hand. American foundries were creating new science through systematic experimentation with materials at unprecedented volumes. Each day's production of 1,000 engine blocks provided more metallurgical data than European craftsmen gathered in months. "We're learning things about iron that no one has ever known," Sorensen reported to Henry Ford during their weekly foundry review. "Mass production isn't destroying quality, it's revealing quality principles that small batch production could never discover." The validation came through endurance testing that shocked European automotive engineers. Ford's test laboratory ran Model T engines continuously for 500 hours, while Mercedes engines failed within 200 hours. The controlled graphite structure was performing exactly as Sorensen predicted, providing internal lubrication that improved with thermal cycling. Wilhelm Maybach studied the intelligence reports from Highland Park with growing alarm. They claim their castings strengthened through use. How is such a thing possible? The answer lay in thermal conditioning that European craftsmen had never observed. Ford's thick-walled blocks absorbed heat cycles that optimized graphite distribution over time. Each heating and cooling cycle aligned the graphite flakes more effectively, creating better internal lubrication. European thin-walled blocks suffered thermal stress that degraded their precision-fitted joints. "Our engines get better with age," Sorensen announced to the Highland Park engineering staff in December 1912. The graphite structure optimizes through thermal cycling in ways that European precision fitting cannot match. By 1913, field data confirmed the laboratory results. Model T engines were regularly achieving 100,000 miles without significant wear, while European luxury engines required rebuilds at 50,000 miles. The difference wasn't craftsmanship, it was materials science applied at industrial scale. The Highland Park Foundry was producing 1,500 engine blocks daily by early 1913, each one containing metallurgical sophistication that traditional foundries couldn't replicate. The specialized milling machines shaped the rough castings with precision that equaled European hand fitting, but at speeds that made Ford engines cost competitive with basic transportation. "We've democratized automotive excellence," Ford observed, watching finished engines roll off the assembly line. "European luxury for American prices." But Sorensen understood that they had achieved something more significant than cost reduction. American foundry science had discovered metallurgical principles that redefined the relationship between materials and manufacturing. The controlled cooling that mass production allowed created iron with properties that artisanal methods could never achieve. European automotive engineers began requesting sample Ford engines for metallurgical analysis. The reports they generated challenged fundamental assumptions about cast iron engineering. Ford's crude American castings demonstrated tensile strength, thermal stability, and wear resistance that exceeded European precision-engineered blocks. "How do they achieve such results with mass production methods?" asked Hans Ledwinka in a letter to Wilhelm Maybach. "Their foundry science appears to surpass our craftsmanship traditions." In Highland Park, Charles Sorensen was preparing for the ultimate test of American metallurgical innovation. The foundry that European engineers dismissed as crude mass production was about to demonstrate engineering superiority that would transform global automotive manufacturing. The chemistry of endurance had become the foundation for industrial revolution. The production numbers that emerged from Highland Park in 1914 defied every prediction European automotive engineers had made about mass manufacturing. By March, Ford Motor Company was completing 230,000 Model T automobiles annually, each powered by an engine block that demonstrated durability exceeding any European luxury vehicle. "Impossible," Wilhelm Maybach declared upon reviewing the intelligence reports. "No foundry can maintain quality at such volumes. The Americans must be falsifying their endurance data." But the data was authentic, and it represented a complete reversal of automotive engineering assumptions. European manufacturers required 6 months to build a single luxury automobile. Ford's Highland Park assembly line completed a Model T every 93 minutes. More shocking still, field reports confirmed that these mass-produced engines outlasted handcrafted European competitors by margins that challenged fundamental beliefs about manufacturing quality. Charles Sorensen stood in the center of the foundry that had become the heart of America's industrial revolution. The operation now consumed 800 tons of iron daily, transforming raw materials into engine blocks with metallurgical sophistication that traditional craftsmen couldn't comprehend. 15 specialized furnaces maintained precise temperatures for optimal carbon distribution. Temperature monitoring systems tracked cooling rates throughout the massive casting operation. "Charlie, we're getting reports from dealers across the country," Henry Ford announced during the April production meeting. "Model T engines are running 200,000 miles without rebuilds. European cars need engine work at 50,000 miles." The numbers represented more than manufacturing success. They proved that American foundry science had discovered metallurgical principles that European craftsmanship traditions had missed entirely. Ford's controlled cooling process created graphite networks that provided internal lubrication impossible in small batch production. The thick-walled design absorbed thermal cycling that destroyed precision-fitted European engines. By early April, chassis assembly time had dropped to 1 hour and 30 minutes. The assembly line integration that European manufacturers considered crude American shortcuts was producing automotive engineering results that redefined quality standards. Workers who had initially resisted assembly line methods now took pride in creating engines that outperformed luxury vehicles, costing 10 times more. "We're not just making cars," P.E. Martin observed. watching the synchronized production flow that moved raw iron to finished engines in 48 hours. We're proving that democratic manufacturing can create superior products. The Highland Park Foundry processed metallurgical complexity at scales European foundries had never attempted. Chemical analysis verified carbon content in every batch of molten iron. Quality control systems monitored graphite formation patterns throughout cooling cycles. Temperature sensors tracked thermal gradients that affected material properties in ways traditional craftsmen had never needed to understand. European automotive manufacturers began experiencing market pressure they had never anticipated. Customers who could afford Mercedes or Rolls-Royce were choosing Model T vehicles because Ford engines demonstrated reliability that European luxury cars couldn't match. The American foundry revolution was reshaping global automotive competition through superior materials science, not just lower prices. Our engines are lasting longer than European luxury vehicles, Sorensen reported to Ford's board of directors in June 1914. The controlled metallurgy we've developed through mass production creates material properties that artisanal methods cannot achieve. Wilhelm Maybach received field reports that confirmed his worst fears about American manufacturing capabilities. Mercedes engines, crafted with centuries of European metalworking tradition, were failing while Ford's mass-produced blocks continued operating. The precision tolerances that defined European quality seemed inadequate compared to Ford's material strength approach. How can mass production create superior durability? Maybach asked his engineering staff. Everything we understand about quality manufacturing suggests the opposite should be true. The answer lay in metallurgical science that European craftsmen had never developed because small batch production didn't reveal the principles Ford's volume manufacturing had discovered. The 24-hour cooling cycles that mass production allowed created optimal graphite distribution throughout cast iron structures. The systematic temperature control produced material properties that individual craftsmanship couldn't replicate. By August 1914, Ford Motor Company was producing over 200,000 automobiles annually, more than all European manufacturers combined. Each vehicle contained an engine block with metallurgical sophistication that traditional foundries couldn't match. The Highland Park Foundry had become the center of a materials science revolution, disguised as crude American mass production. Field endurance data continued validating Sorensen's metallurgical innovations. Model T engines were regularly achieving 300,000 miles, while European competitors required multiple rebuilds during similar service periods. The graphite networks that Ford's controlled cooling created were providing internal lubrication that improved engine performance over time. European automotive engineers began requesting detailed specifications for Ford's casting process, hoping to understand how American methods achieved superior results. The intelligence they gathered challenged fundamental assumptions about the relationship between manufacturing speed and product quality that had guided European industry for centuries. They've discovered metallurgical principles we never knew existed, reported Hans Ledwinka after analyzing Ford engine samples. Their foundry science surpasses our craftsmanship traditions through systematic understanding of materials at industrial scale. But on September 23, 1916, disaster struck Highland Park with devastating force. A massive explosion in the foundry's main casting area killed 11 workers and destroyed 3 months of production capacity. The blast sent molten iron cascading through the facility, melting specialized machinery that had taken years to develop and install. Sabotage, Sorensen concluded, examining the wreckage of what had been America's most advanced foundry. European competitors couldn't match our engineering, so they destroyed our capacity. The explosion wasn't mechanical failure. Forensic investigation revealed deliberate tampering with foundry safety systems. European manufacturers, unable to compete with American metallurgical innovation, had resorted to industrial warfare. Orders canceled immediately. Stock prices collapsed. Critics proclaimed it proof that American manufacturing shortcuts inevitably led to catastrophic failure. The foundry revolution that had redefined automotive engineering faced its darkest hour. But Charles Sorensen was already planning the comeback that would prove American foundry science could survive any challenge European competitors could mount. The reconstruction began at dawn on October 1, 1916. Charles Sorensen stood in the ruins of what had been America's most advanced foundry, surveying damage that European competitors believed would end Ford's metallurgical revolution forever. Twisted steel beams and melted machinery created an industrial graveyard where molten iron had cascaded through the facility during the explosion that killed 11 workers. Charlie, the insurance company is calling it an act of war, Henry Ford said, examining forensic reports that confirmed deliberate sabotage. European manufacturers couldn't compete with our engineering, so they destroyed our capacity. Sorensen nodded grimly, his hands already sketching reconstruction plans that would transform disaster into opportunity. Then we rebuild better than before, stronger foundry design, improved safety systems, metallurgical controls that no saboteur can compromise. The Highland Park Foundry reconstruction became a testament to American industrial resilience. Sorensen designed revolutionary safety systems that isolated foundry operations into compartmentalized sections, preventing any single explosion from destroying entire production capacity. Automated fire suppression systems used pressurized carbon dioxide to extinguish molten metal fires within seconds. Emergency ventilation systems removed toxic gases faster than workers could be exposed. We're not just rebuilding, Sorensen explained to the engineering team assembled in temporary headquarters. We're creating the world's safest foundry while maintaining metallurgical precision that European competitors still cannot match. By December 1916, the new Highland Park Foundry incorporated safety innovations that redefined industrial manufacturing standards. Blast-resistant walls contained potential explosions within designated areas. Multiple temperature monitoring systems provided redundant thermal control throughout casting operations. Chemical analysis equipment verified iron composition continuously rather than batch by batch. The metallurgical improvements surpassed even Sorensen's original innovations. New furnace designs maintained more precise temperature control during 24-hour cooling cycles, creating optimal graphite distribution throughout cast iron structures. Automated quality control systems monitored material properties in real time, ensuring consistency impossible in European artisanal production. Our new blocks are testing at 30,000 pounds per square inch tensile strength, Sorensen reported to Ford in January 1917. 20% stronger than our previous castings and 50% stronger than European luxury engines. The reconstruction had transformed catastrophe into metallurgical advancement. European sabotage intended to destroy American foundry capabilities had instead accelerated innovations that widened the performance gap between Ford's mass-produced engines and European handcrafted competitors. Wilhelm Maybach received intelligence reports about Highland Park's reconstruction with growing despair. They've rebuilt stronger than before. Their new foundry incorporates safety systems we've never imagined, while maintaining metallurgical capabilities that still exceed European craftsmanship. Ford Motor Company resumed full production in March 1917, producing engine blocks with durability that field testing confirmed surpassed all previous achievements. Model T engines were now regularly achieving 400,000 miles without significant wear, while European luxury engines continued requiring rebuilds at 50,000 miles. The new foundry incorporated automated systems that European manufacturers couldn't replicate in artisanal production. Robotic material handling moved castings through cooling cycles with precision timing that optimized graphite formation. Computer-controlled temperature monitoring maintained thermal conditions throughout massive casting operations. Quality assurance systems tested material properties continuously rather than sampling individual components. We've created industrial science that artisanal methods cannot match, Sorensen observed, watching the synchronized operation that transformed raw iron into metallurgically sophisticated engine blocks. European competitors destroyed our original foundry, but they accelerated innovations they'll never duplicate. By 1920, field data provided ultimate validation of American foundry science. Model T engines demonstrated average service life exceeding 300,000 miles, while European luxury automobiles averaged 50,000 miles between major rebuilds. The controlled graphite networks that Ford's cooling process created were providing internal lubrication that improved engine performance throughout extended service periods. European automotive manufacturers began licensing Ford's metallurgical processes, acknowledging that American foundry science had surpassed centuries of European craftsmanship tradition. Mercedes-Benz purchased Ford casting equipment. Rolls-Royce hired American metallurgists trained at Highland Park. The Sabotage, intended to preserve European automotive superiority, had instead accelerated American technological dominance. They've proven that democratic manufacturing creates superior products, Wilhelm Maybach admitted in his final report to Daimler Motoren Gesellschaft. American foundry science discovered metallurgical principles through systematic experimentation that European artisans never developed through individual craftsmanship. The ultimate vindication came through endurance testing that European manufacturers had never attempted. Ford engines ran continuously for 500 hours, while Mercedes competitors failed within 200 hours. The material science that mass production had revealed created durability that traditional craftsmanship couldn't achieve through precision fitting and individual attention. Charles Sorensen's Foundry revolution had survived industrial sabotage to prove that American innovation could create engineering superiority through scientific understanding of materials at unprecedented scales. The thick-walled cast iron blocks that European engineers had dismissed as crude American shortcuts were outlasting handcrafted luxury engines by margins that redefined automotive quality standards. By 1925, over 15 million Model T automobiles powered by Sorensen's cast iron engines traveled American roads. Field maintenance records confirmed average engine life exceeding 300,000 miles, while European luxury vehicles continued requiring rebuilds at 50,000 miles. The metallurgical science that Highland Park had developed through mass production had created automotive durability that individual craftsmanship could never match. The tragedy that European competitors intended to end American foundry capabilities had instead accelerated innovations that established United States manufacturing superiority for the next century. Charles Sorensen's cast iron engines proved that democratic industrial methods could create products superior to aristocratic European craftsmanship through systematic application of materials, science at scales traditional foundries had never imagined possible. American foundry science had not only survived European industrial sabotage, it had transformed catastrophe into engineering triumph that would define automotive manufacturing excellence for generations.